You go to Billings for some new clothes. You buy 3 shirts, 4 pants, 2 hats. Each item costs $3. How much did you pay total? We know the answer is $27. We know that. But how did we get there is the question. Does somebody want to share how they got there? Go ahead. Okay, so you said, if I understand what you're saying correctly, you took the 3 shirts plus the 4 pants plus the 2 hats, right? And then if I'm using GEMS, order of operations, I add those things together and I multiply times the dollar amount, right? So $3 times that. Is that pretty much what you did? Did you actually write that down like that? Or did you just go 3 plus 4 plus 2 is 9, and then next line down or something, you added the 3 in and said 3 times 9 is 27. Okay, so that's what you did though. Verbally, this is what you told me. You added them together and then you multiplied times 3, right? Did anybody do something different for this? Go ahead.
Multiplied 3 times 3 and 4 times 3.
All right, so what you did is you said, I have 3 shirts and each shirt cost me $3. So that means I spent how much in shirts? I spent $9 in shirts, so 3 times 3. And then I have to also add on how much I spent in pants, which was 3 times 4, right? 4 pairs of pants, each one was $3. And then I also have to add on how much I spent in hats. $3 times 2 hats. Does this one give me $27? Yes, it does. Does this one give me $27? 3 times 3 is 9. 3 times 4 is 12. 3 times 2 is 6. 9 plus 12 plus 6 is 27. Both of these give me $27. Does that mean that one is better than the other? No, actually they're both the same. In fact, this is exactly the same thing as that. I'm putting in, that's an equal sign that's up and down. That's what we're doing in this section, actually. You guys, two different people came up with the same way to solve something, and this is actually a property that we're studying in this section. What happened here is the distributive property. I'm just going to show you here real quick. You've probably seen it before. I don't know for sure. Has anybody seen the distributive property before? The distributive property means that you take the thing that's outside being multiplied into a bunch of stuff, and you distribute it to each one of those being multiplied. So 3 times 3. Look right here, 3 times 3. 3 times 4, 3 times 4. 3 times 2, 3 times 2. We had addition going on here, addition. Addition going on here, addition. This is the distributive property. You can send in that thing on the outside, and it will give you an equivalent statement. So I'm going to step away from numerical expressions for a minute here, and we're going to go to geometry. Look at the 2 figures. What is the overall area of each of these figures? So let me ask you this. How could we figure it out? How do you find the area of something? Okay, so if we have a rectangle, to find the area, need area equals, some of you have called it base times height, or you could say area equals length times width, I just heard. Right? You've seen that before. I know that for a fact. So we can find the area of this rectangle right here. In order to find the area, we're going to multiply the base times the height, or the length times the width. And we know that we can do width times length because the commutative property for multiplication works. So I could write x plus 5 times 8, or I could write 8 times x plus 5. You guys agree? It doesn't look like a number. Like if I had a 4 here, it'd be 8 times 4. It's no big deal that I don't have what I normally am used to seeing. Now I have some sort of algebra going on here. It's still the same property. This times this. So we write 8 times that length. So with the second figure then, how could I come up with the total area of what I'm looking at? Go ahead.
8 times x plus 5 times 8.
So you're looking at this as two separate things, and we put them together and we get the total area of the figure, right? Does everybody see that? If I find the area of this one and I find the area of this one and I add them together, I'll have the total area of the figure. So we split it up, and we have 8 times whatever this length is, x, and then we're going to add on whatever the area of this is. To find that area, we go 8 times 5. So if you look at this, we have 8 here and then x plus 5 here. Here we have 8 again, so the height of this rectangle is the same as the height of this rectangle. X plus 5 on the base. Here this is a distance of x, and this is a distance of 5. So what is the total distance here? It's x plus 5. This distance x plus this distance 5. Add it together and you get x plus 5. So is this rectangle the same as this outer rectangle here? Yes, they have the same dimensions, which means they have the same area. So I can put an equal sign here. And now once I do that, look at the difference between what I wrote here compared to what I wrote here. Do you see the distributive property happening? 8 times x is 8x. 8 times 5 is 8 times 5. There's a plus sign in between. There's a plus sign in between. You've now seen two different ways that you can do distributive property. And we're going to be using it all year. Almost every day. So you're going to get used to it pretty quick. All right, I have one more thing that I can say about the distributive property. I don't know if Angry Birds is so much popular anymore as it used to be a few years ago, but it's a lot like Angry Birds when you draw the little arcs that go from the front thing to the back. In Angry Birds, you see the little tracer that goes as the bird flies through the air. It's a lot like this. This is my bird, and I'm firing it, and I'm trying to hit that guy. Then my bird, I fire it, and I try to hit that guy. And what I'm really doing here is I'm multiplying. So A times B gives me AB. Then I come back here and I fire this one. A times that positive C gives me positive AC. That's the distributive property. So if you want to think of it like Angry Birds, go for it. Do we all play Angry Birds still? Or is that kind of has that faded out? They keep coming out with new ones to keep you addicted. I think it's a fun game. That was totally different though, wasn't it? Flappy Birds?
Yeah, it is.
Way different. It's more like Super Mario Brothers or something, right? All right, anyway. For example, let's do these problems two different ways. Let's do it using order of operations. So gems. Gems would tell me inside the grouping symbols first, and then multiply what's outside. Distributive property tells me that I can send that thing that's outside in, and multiply those two numbers together, and then simplify once I'm done. So let's do it the gems way first. If I'm following gems, then what happens first here? Inside the grouping symbols becomes 7. So I have 3 times 7, which is 21. All right, so we know our answer is going to be 21. Let's use the distributive property now to see if we come up with 21. So let me draw a line here, just so that I have room underneath and we don't get confused. So I'm going to use the distributive property. This is 3 times some stuff inside a grouping symbol. That's when you can use the distributive property. It has to be multiplication right here. If you see addition or subtraction, you can't distribute. If you distribute, you're going to get the wrong answer. So we can distribute here. 3 times 2 is 6. And then come back up here. 3 times positive 5 is positive 15, so I'm going to write plus 15. And now 6 plus 15 is 21. Did we get the same answer? Yeah. If you see a plus sign right here in between, or a minus sign in between, then that's not the distributive property, okay? It has to be something times some stuff. That's what I was trying to say. If you see subtraction here, like we're about to have here, that's fine. It's here that it must be multiplication, all right? I see a lot of people make mistakes there, so that's why I'm bringing it up. All right, Let's go ahead and distribute on this one first. So we're not going to use gems this time. What do we get for our first distribution? 4 times 9 is 36. And then we come back over here and do what? 4 times -7. The sign stays with the number. If you get confused by that, we could always do a change here, and you can see that that's a -7 sitting there. Okay? So it's 4 times -7, which is -28. So I'm going to write minus 28. Negatives and subtraction symbols are the same thing when you are working with some sort of expression like we have here. So now we have 36 minus 28, which is what? 8? All right, I'll write down 8. 5? It's 5. No, it's 8. Let's go back up here and check. The original problem was 9 minus 7 in the grouping symbol. 9 minus 7 is 2. And then we have 2 times 4, which is 8. So we get the same answer both ways again. All right. The point, though, is to use the distributive property. So that's why we're doing the distributive property here. Let's try this one now. A little bit trickier because of that, what? The negative sign out front is tricky. So we have a -2 that we're multiplying in. What do we get when we do this? That's -2 times +5, which is what? It's -10. And now we have -2 times what? What is -2 times -8? It's +16. So I'm going to write what? Plus 16. Now what do I get as my answer? I get 6, and it's positive. The 16 is bigger, so I keep the sign of the bigger number. Let's double check this real quick. What is 5 minus 8? It's -3. So -3 times -2 is +6. We get the same answer both ways. Now, I'm showing you that because I want to show you that gems works. The distributive property works. Eventually, we're going to get to the point where it's not just numbers in here. We're going to have letters in here too. And we're still going to be able to distribute using those letters. Okay? All right, are these statements true? We have AB plus AC equals A times B plus C. Is that a true statement? Here's some yeses. For those of you saying yes, why is that a true statement? Oh, so you're looking over here, and you're saying this is the distributive property here, and I get AB and AC when I distribute, right? Yes. This is actually written backwards. You guys all see that? So it's just the distributive property backwards. There's a property that allows us to do that. It's called the symmetric property. This actually is where we're going to be after in second semester. We're going to be starting with problems that look like this, and we're going to be doing something called factoring, which is just undoing the distributive property, kind of like subtraction undoes addition. We're going to undo the distributive property and wind up with something that looks like this as our answer. So that's coming up. Right now we're going this way. Later this year we'll go backwards. How about this one? B plus C, and then times A equals AB plus AC. Is that one true? Heard a couple yeses and a couple nos. Anybody who thinks it's true really think it's true, and they want to explain why? Anybody who said no really believe that it's no, and they want to explain why? So these are yeses. Why? The answer is yes, but why? When I multiply stuff, does it matter what order I multiply them in? No. So even though this looks like a lot of stuff going on here, what's really happening is I have this thing times this thing. That multiplication can be reversed, which means I can put that A out here. And then once I do that, don't I have exactly what I have written right here? Yeah. You can distribute forward like this. You can also distribute backwards. If you have something behind that you want to distribute in, you can do that. A times B is AB. A times C is AC. That's why we study those properties, so that you guys can see that this actually is true. So both of these statements, it turns out, are true. Now we have algebra sitting here. There's letters involved in these. So you just took a vocab quiz. We were working with numerical expressions. These are now algebraic expressions because of the letters that are involved. Do you see X in every single one of them? No. It doesn't matter what the letter is, right? It's just a variable. So we can use the distributive property in an algebraic expression. To do that, what's 7 times 3W? Good. It is 21W. And now I haven't really talked about that so much yet, but what happened to get 21W? You multiply 7 times 3. It's like this. Think of it this way. If I had a bag, one bag with 3, apples in it, okay? And now I multiply that bag times 7. So now I have 7 bags. Each bag has 3 apples in it. How many apples do I have? 21, all right? Same thing happened here. I have 3 W's here, and now I'm multiplying that 3 W's times 7. So I wind up with 21 W's. Continue the distributive property. What do we get? It's a negative 35. That's a negative 5. 7 times negative 5 is negative 35. So I write minus 35. And that's the answer. For the next one, what should we do? Distribute. Yeah, the 5's on the other side. Does that matter? No, it doesn't matter. So we take the 5 and we distribute. What do we get here? Good. 30V plus 3 times 5 is 15. Now, do you need to draw those little arcs above the problem? No. But if you have to, because it helps you, then absolutely. I'll be doing it for a while, and then eventually I'll stop doing it. But I teach calculus too, and sometimes I'll draw those in there because we need to see it. So that visual helps a lot, even for a math class like calculus. Can I add these two things together, 30V plus 15? I can't. We're going to talk about what's called like terms here in this section. These cannot be added together. This is 30 V's. This is just 15. I can't put those together. This is like 30, tulips, and then this is 15 pieces of concrete. You can't add those together. They are separate things. So we have to leave them apart. Okay? If there was a V here, could we add those together? Yes. And like I said, we'll talk about that here in a little bit. I just want to point that out now. All right, this one's kind of tricky looking. We have a negative sign sitting out front. Is it just a negative sign kind of hanging out? That's actually a -1. Good, I like that. Anytime in algebra you don't see a number in front of a variable, you can assume that there's a 1 there. We typically don't write the 1. So like off to the side, 1x is the same as just writing x. We're just assuming that there's that 1 there. So here, without that number out front, we're going to assume there's a 1. So technically I'm distributing a -1 in. So what do I get when I distribute that -1 in? Positive 2x, because a negative times a negative is positive. And then what? So for my second part, minus 5, because -1 times positive 5 is -5. And again, can I add those together? Can't do it. Those are not like terms, is what we would say. So you can't add them together. And right here, like terms. So anytime you use the distributive property, your next step is going to be to look to see if you can do what we call combine like terms. We didn't have any like terms here, or here, or here, so we couldn't combine them. But if we did, then we would have to combine them right then. All right? So you will hear me say, what is the next step after we do the distributive property? And then you will say, combine like terms. And we're going to say that all year long. Okay? Like terms have two important features. There's variables and there's exponents in any term. The variables have to be exactly the same. So if I had a variable of x, or I had a term that said like 5xy, then I better see xy in some other term if I'm going to call them like terms. They have to be exactly the same letters. And the exponents have to match on each of those letters. The exponents have to match on each variable individually. So if I see, let me see, is there examples here? Okay, if I had just off to the side, I'm going to put an example up here, x squared times y. And then I have plus 4xy squared. Are these like terms? Do I have the same letters? Yes. Do I have the same exponents on each of those letters? No. Here I have x squared, y. Here I have x, y squared. These are not the same. So they're not like terms. You can't add these together. If I had another term like 3x squared y, would these now be the same? Yes. And then I could combine them. And we'll talk about combining like terms here in a little bit once we get there. But the answer here would be, there's a 1 here. So if I add these together, I'd get 4x squared y. What do you do with the coefficients when you combine like terms based on what I just said? You add them. When you see a minus sign, think of that minus sign as adding a negative number. So that when you combine like terms, here, if you see 1x squared y plus 3x squared y, you get 4x squared y. But if I saw negative 1x squared y plus 3x squared y, I add those two numbers together and I get what? 2. If I add 3 and negative 1 together, I get 2. Okay? We'll deal with like terms a lot, so if you don't understand that just yet, we'll get to simpler examples here. All right, let's do these example problems here. Simplify each expression. So you need to look to see if they're like terms, and if they are, then combine them, okay? So is 17u and 25u, are those like terms? Yes, they have the same letters, and the exponents are exactly the same. So we can combine them, which means we're going to add the coefficients, the numbers out front. 17 plus 25 is 42. And then I got to include the variables that were attached to that, so it's 42u. It's kind of like if I had 17 apples plus 25 apples, I'd wind up with 42 apples. You can think of this as 17 u's plus 25 u's. I have now 42 u's. How about 6t squared plus 3t minus t? Do we have any like terms here? If it's going to be a like term, the variables have to match and the exponents have to match, right? So take a look at the t squared here. Do I have any other terms that are t squareds? No. So there's no like term for that guy, so I'm just going to write it down, 6t squared. Now I have these two terms here, 3t minus t. Are those like terms? Are the variables the same? Yes. Are the exponents the same? Yes. So they are like terms. This is 3t minus 1t, which gives me 2t. So I'm going to write, that's a positive 2, so plus 2t. Again, think of it in terms of apples. 3 apples minus 1 apple is 2 apples. So 3t minus 1t is 2t. The variable does not disappear. How about 6n minus 4n? Are those like terms? You get 2n. Good. How about b squared plus 13b plus 13? Do we have like terms there? See a lot of heads shaking no. Some people are saying no. We have b squared. There are no other b squared terms. So that one does not have any like terms. We have 13b, but this does not have a b on it. So that's not a like term either. And then we have just a number here. This does not have any like terms. In fact, that is already simplified. Do we have any like terms on the middle one in the bottom row? The 2y and the minus 8y. That's right. So the 4y cubed does not have any like terms. So we write it down. We have plus 2y and minus 8y. When we combine those, what do we get? It's, what's the sign? It's negative 6. So we're going to write minus 6y. Think of them all as addition. I have 2y, and I'm adding negative 8y to it. I get negative 6y. And then we have this plus 5. There's no like terms for that one, so we just write down plus 5. That's the answer. Finally, for the last one, do we have any like terms there? Yeah, what do we got? The 7a and the negative 2a combine, what do you get? That's good. 5a, that's right. We have 7a, and then really that says minus 2a. 7 minus 2 is 5a. What else? The 4 does not have any like terms, so I can write that down. And that's a negative 6a squared, so I'm going to write minus 6a squared.